All right, this is a typical question that you will see, kind of a go-to question maybe in a homework or quiz. So we're going to be told this limit up at the top. The limit of 10x plus 1 as x approaches negative 1 equals negative 9. And they go ahead and tell us what it equals. Of course, we could plug that in and we could see, yeah, that gives negative 9. Okay. All right. So based off of that, let's find the value of delta that corresponds to epsilon equals 0.02. Okay. So we're told the value of epsilon. That's how close we need our function to get to negative 9. How close must x get to negative 1? That's what we're looking for, the value of delta. Okay, how are we going to set this up? So if you remember, let me go back to the precise definition. We're going to set it up just like this here. We know our function. We know what L equals. L is what the limit equals. And we know a value of epsilon to plug in. And then we're going to do some algebra on that to end up with something that looks like this. Then we'll know delta. That'll be our final answer. Okay, let's walk through it. Okay, so we're going to, okay, well, I guess I wrote that out again. We're going to set it up like this. All right, so I know my function, that's L, and of course, my value of epsilon. I'm going to plug all those in. By the way, I've got a graph over here. Ignore that for now. I'm going to talk about that at the end of this part A. Okay, so I'm plugging all these parts in. There's my absolute value. My function minus negative 9 less than 0.02. We're going to begin just by simplifying here. And it turns out it's 10x plus 10. Still less than 0.02. We're going to factor out the coefficient on x. Factor out that 10. Okay. And the very last step, all we got to do is divide. And that's going to end up being the delta. One thing I should point out, let's rewrite this left side so it looks more like the definition from a moment ago. X minus a. And our a in this case was the negative 1. X was approaching negative 1. Okay, so that last line looks like the very end of the precise definition. X minus a is less than delta. Delta is 0.02. So if you want your function to be within 0.02, delta, you need x to be within 0.002 of negative 1. Let's go to my graph over here. What does this mean graphically? Okay, so I have that function graphed, at least a sketch. That's 10x plus 1 going through 1 there on the axis. It's got a slope of 10. I kind of made it a bit more mild. Slope of 10 is not the easiest thing to draw or to visualize. Okay, so we know when x approaches negative 1, the limit is negative 9. So I'm just going to go ahead and plot that point. And I'm going to create this little window around negative 9. What values would those be in this example? So we said to be within 0.02. So this upper one, if we add 0.02, that would be negative 8.98. And down here, well, that's negative 9.02. So we moved 0.02 in either direction. If we were to trace this back to the function and then up, it creates a little window around negative 1. And where would these values occur? I think it's too small to squeeze in. It's that far away. So negative 1 plus 0.002, negative 0.998, and on this side, negative 1.002. So if we get x to be within there, then our function's going to be within here. And that's the visual for these values of epsilon and delta with this function and this limit. Okay, very nice. Well, that was part A. What do I have in part B? Kind of a natural follow-up. Let's find the value of delta for any epsilon. We're not going to give it a value. We're going to say any value of epsilon you pick, any small number. What's the value of delta? And we're really looking for the relationship between epsilon and delta. Well, it's going to look very similar to what we just did. We just don't have a number for epsilon. So we're going to go ahead and start the same way. Absolute value 10x plus 1 minus negative 9 is now just less than epsilon. And so we'll go ahead and clean that up a little bit. And still factor out the 10. Divide by the 10. And there we've got it. X plus 1, really that's x minus negative 1. This is what we're after. Epsilon over 10, that's what delta is equal to in this case. So whatever value of epsilon you pick, divide it by 10. And that's the delta you need. Hey, did you guys, what is 10? What is 10 back in this problem? Isn't that the slope again? The slope of that line is 10. So if we, this width here is 10 times as big as this width because the way the slope works when we draw those lines. Yeah, I mean, that's kind of nice to see it. You don't really need to know that. But it's, it's sort of connecting all the dots. Okay, we have one more example. We're going to take it up a notch. Here it is. Let's take the limit of x squared minus 3x plus 1 as x approaches 4. And you could tell if you were to plug 4 in, well, that would give you 5, the answer to this limit. Okay, what are we going to do with that? Find the value of delta that corresponds to epsilon equals 0.5. And we're going to have to round. Well, it looks like, hey, this is really the same kind of question we just saw. We're given a limit. Find the value of delta that corresponds to this value of epsilon. What makes this more difficult or challenging than the previous problem? We have a quadratic. And, well, it's one thing to be a quadratic, but it's not a line. I'll say that. It's not a straight line. So because this thing is curving, that makes the concept a little bit trickier. But we're going to walk through it and talk about it. Okay, so part of our approach, it's going to change from the very beginning. And I've just got this note here. I'm actually going to change this. We're not going to find delta solving that absolute value equation using absolute values because our function is curved. It's not a straight line. A straight line is great because we can always factor out the slope, divide, and we get the relationship between epsilon and delta. But when it's curving, that's a different story. But no problem. We've got just a different approach here. Here's what we're going to do. We're actually going to set it up more like, or really just like the way we did this, the way I introduced this way at the beginning of the section. So we're going to say, hey, if we want our limit to be within 0.5, we're just going to take 0.5 above and below this number here. Okay? Just like this. So maybe this looks familiar. This style. This is how we began the section way back. Okay. So with 5, I'm going to add and subtract 0.5, so I want my function to be somewhere between 4.5 and 5.5. Okay? So what are we going to do with that? Well, it turns out we're not going to isolate x in the middle or anything. That would be far too difficult. We're just going to say, hey, there's a lower boundary, 4.5, and there's an upper boundary of 5.5. We know we're caught somewhere in the middle. We're going to approach it like this. We're just going to set our function equal to the lower boundary and solve this. And we're going to take our function and set it equal to the upper boundary and solve this. It's going to be a little bit more work than those previous examples because it's not a line. We can't just factor something and divide and boom. But you know, it's gonna work well for us if we just set it equal to each of these extreme values on the low end and the high end. Okay, so I'm gonna walk through the lower boundary and then just know the upper boundary plays out in a similar way. I'm actually, well, okay, let's see. I'm saying too much. How does it play out with the lower boundary? Well, if we want to solve this quadratic equation, let's set it equal to 0. I'm going to subtract the 4.5 over here. And, well, I might as well comment because we can see it. We're subtracting the 5.5, right? Setting it equal to 0. And here, well, I recommend you don't factor. That wouldn't go over too well. Just use the quadratic formula on this. We're going to have to round it to 3 decimal places. Okay. So if you remember, x equals negative b plus or minus square root b squared minus 4ac all over 2a, like so. And I won't really spend any time breaking this down. I'm just going to clean up what's inside that square root. Turns out it's 23. So I've got positive 3 plus or minus the square root of 23 over 2. And this, of course, leads me to 2 answers when I add and when I subtract. So if I'm to add and divide by 2, and I went ahead and just rounded all these to 3 decimal places, 3 plus square root of 23 over 2 gives me this, 3.898 when it's rounded. If I subtract 3 minus square root 23 over 2 gives me this, negative 0.898. And then you can see I did not show the details here. You would use quadratic formula again. I'm just gonna skip down to the answers. I trust, if you guys want to check these, I trust that you can use quadratic formula on that and get to these same x values. Okay, so where to go from here? It turns out in each pair, we only want one of those solutions. Okay, so if you guys remember, this whole question was about x approaching 4, right? And the whole idea is we want to find delta. Delta is how close we need to get to 4. So in each pair, you see a number that's close to 4 and one that's not. So these numbers that are not close to 4, they end up being solutions to those, but we don't need them to get further in our problem. So we can just ignore the negative 0.898 and the negative 1.098. Focus on the numbers that are very close to the 4. Okay. One's a little bit lower, one's a little bit higher. That makes sense. This came from the lower boundary, this from the upper boundary. Okay, where to go from there? Okay, I'm going to repeat what I just wrote there. We've got our lower boundary of x and we've got our upper boundary of x. Okay. So if we pick this x value, our function would turn out to be 4.5. If we pick this x value, our function would be 5.5. I'm going to graph these values on a number line, okay? Like so. Like, why are we doing this? So here's 4. This is what x is approaching, right? We've got our lower boundary and our upper boundary. It makes this kind of little, this little interval around 4, right? Here's the thing. Here's why I draw this. Delta is always just one number. Think of the distances from 4 in either direction. Okay? They're not equal here. And I even tried to draw this one a little bit bigger because this number is a little bit further away than this one is. So let me highlight that. From 3.898 to 4, that's a distance of 0.102. And the distance from 4 to 4.098, well, that's, of course, 0.098. You think, well, are there 2 different answers? Like if you're below, then delta is this, but if you're above, then delta is this? No. There's only one number for delta. Delta needs to be symmetrical, around 4. It could be above by that distance or below by that distance, but it's got to be the same distance. So which of the 2 numbers, we're going to pick one of them to be delta, or I should say one of them is delta. Which of these is delta? Do we pick the bigger number or do we pick the smaller number? And I'll just tell you, we're going to pick the smaller number. And I'll explain why. So our answer is going to be the lesser one. And I kind of given you the reason right here. It works in both directions. So in this case, when your function is curving, then you're going to get this asymmetry. But you always pick the smaller number. Whichever side it's on, you pick the smaller number, the smaller distance to be delta. Why? If you were to pick the smaller number, then all the x values within that smaller distance are going to land your original function within your specified epsilon. Okay? In other words, if you pick the smaller one, it always works. It works in this direction right up to the border. It works in this direction with a little bit of room to spare. Okay? If you were to pick the bigger number, why would that be wrong? Well, the bigger number would be fine in the lower direction, but the bigger number in this direction would go beyond, and it would allow for some x values that actually do not satisfy your requirements for epsilon. The bigger number would allow some values of x up here that are outside your upper boundary. And so what we do is like it's kind of like we hedge our bets, or we play it conservatively. We take the smaller one because that one will work in both directions with a little bit of room to spare on one side. So in conclusion here, delta gives a symmetrical interval around x equals 4, and it's got to work for all those values. So we pick the smaller one. Okay, that is section 2.4. Go check out the homework. Bring your questions to our Zoom meeting, and good luck.